Atoms, Part 3, the Bohr Model. We have seen how the model of the atom has been modified from the Greeks to Dalton and then to Rutherford's nuclear model. An atom has protons and neutrons in the nucleus. These particles carry essentially all of the mass, and tiny electrons on the outside. Rutherford also found that atoms are mostly empty space. In order to understand the next step in the development of the modern model of the atom, we need to take a short side trip to talk about light waves and energy. Light is made up of waves. There are several measurable characteristics of waves, of which we are interested in 3. Wavelength is the distance from one crest to the next. The symbol for this is the Greek letter lambda. Velocity, or speed, is how fast the wave is moving, symbolized by v, or, in the case of light, c, the symbol for the speed of light. And frequency, which is how often a crest passes any given point, and is symbolized by the Greek letter nu. If you think about a wave moving at a constant velocity, how often a peak passes a certain point depends on the wavelength. A longer wavelength will have a smaller frequency. Fewer crests will pass in a given time than if the wavelengths were shorter. So, frequency equals the velocity divided by the wavelength, or nu equals c over lambda. If you pass white light through a prism, it breaks into the colors of the visible spectrum. Each color has a different wavelength, as shown in the scale along the bottom of this picture. Here, shorter wavelengths are on the left, and longer wavelengths are to the right. This only shows the visible spectrum. The full spectrum shown here shows that shorter than 350 nanometers would be ultraviolet radiation, X-rays, and then gamma rays. And to the right of 750 nanometers, red, would be infrared, microwaves, and radio waves. As we saw in class, however, individual elements do not produce a continuous spectrum when electricity is passed through them. Each element has its own unique line spectrum, and these spectra are used in astronomy, archaeology, environmental science, and other fields to identify component parts of samples. To understand why elements do not produce continuous spectra, we need to learn a little bit about quantum mechanics. Max Planck first proposed that the energy of electromagnetic radiation comes in small packets he called quanta, or singular quantum, and that the energy of a quantum of radiation is inversely proportional to the wavelength of that radiation. Energy equals a proportionality constant times the velocity, in this case c, divided by the wavelength, or E equals a constant times c over lambda. That constant is called Planck's constant, and its symbol is h. So, E equals hc over lambda. This means that as the wavelength increases, energy decreases. So if we go back to our visible spectrum, we can see that red light has less energy than blue or violet light. Red energy has a longer wavelength, and so a lower frequency and a lower energy. After Planck's idea that energy is quantized, Einstein hypothesized that electromagnetic radiation has both wave and particle characteristics. A particle of light is called a photon, and a single photon has an energy of hc over lambda, just as Planck had said. After Einstein's idea that energy has particle characteristics, Louis de Broglie proposed that matter also has both wave and particle characteristics. These wave characteristics only show up in extremely small particles, such as electrons, however. This is because, according to de Broglie's hypothesis, the wavelength of a particle is inversely proportional to its mass and its velocity, with the proportionality constant being, once again, Planck's constant. So the larger the mass, the smaller the wavelength. Anything macroscopic, visible to the eye, has a vanishingly small wavelength, so that its wave properties are undetectable. So, what does this have to do with atomic structure? Niels Bohr hypothesized that if electrons have wave properties, including wavelengths, then for an electron to fit in a space around the nucleus of an atom, its wavelength must be such that it forms a closed loop. If it doesn't, the waves will destructively interfere as the electron moves around the nucleus, thereby becoming unstable. So the wavelength of an electron in an atom must be a whole number multiple of the circumference at its distance from the nucleus, or 2 pi r equals n times lambda, or the wavelength, where n is a whole number, 1, 2, 3, etc. This n will be our first quantum number as we begin to describe electrons in the quantum model of the atom. But the wavelength is related to the energy, so electrons can only have specific energies that allow their wavelengths to fit at specific radial distances from the nucleus. This now allows us to explain the atomic line spectra. An electron at its lowest allowed energy state, with its longest allowed wavelength, can absorb energy if, for example, electricity passes through the atom. If the electron absorbs the right amount of energy, it can move up to a higher energy level, a level that allows for the new, higher energy, and so shorter wavelength. If that excited electron then loses that excess energy, it will drop back down to its original, or ground, state. That excess energy is then emitted as a photon of light. An electron transitioning from a higher to a lower energy level emits a photon at a specific wavelength related to the number of energy levels it is dropping. If the light emitted from a sample of an element being excited by electricity is passed through a prism or a diffraction grating, those emitted photons are seen as the characteristic line spectra for that element. Excited electrons, dropping down to their ground states, emit specific wavelengths of light.